Hello everyone. Today we will showcase a demo on enabling 5G Dynamic TDD by leveraging deep reinforcement learning and Open Run. This demo is accepted and will be presented in ACM Mobile conference. First, we will show the motivation behind this demo. Then we will go through a main overview about different components involved in this demo, and finally we move to the actual demo. As you may notice, 5G and beyond services are shifting from downlink dominant traffic to more equilibrated downlink and uplink traffic or uplink dominant traffic. To accommodate this new type of behavior, 5G NR allows a complete flexibility to define the TDD uplink downlink pattern. This flexibility is called Dynamic TDD. Dynamic TDD allows the GNodeB to change the TDD configuration on the fly to adapt to the traffic pattern. The TDD configuration consists of the number of downlink slots and the number of uplink slots and the slot configuration period. Changing the TDD configuration allows to allocate more downlink and uplink slots to accommodate the new behavior of 5G and beyond services. However, 5G NR specifications only cover the mechanism allowing the GNodeB to define the TDD period and inform the UEs about the uplink and downlink slots, which makes the algorithm deriving the pattern still open. To fill this gap, we propose a deep reinforcement learning-based solution that allows the GNodeB to self-adapt to the traffic pattern and allocate more uplink or downlink slots. The DRL solution will run on Open Run Rig near real time. It monitors the status of uplink buffers and downlink buffers via the E2 indication messages. Then it will execute the DPG algorithm to derive the percentage of uplink slots and send the results via E2 control message. The GNodeB will update the TDD configuration and inform the UE about the new configuration. Let's move to the demo. In this demo, we'll use OpenR interface standalone GNodeB configured with 20 MHz of bandwidth and operating on numerology 1 with a TDD period of 5 milliseconds, which makes 10 slots per TDD period. Then the XUp will divide these 10 slots between uplink and downlink. We will use two UEs based on QuickTime modules. Let's connect them to the GNodeB. Connect the first UE. Then let's connect the second UE. And let's open the TDD XUp and run it. Here, the TDD XUp monitors the uplink and downlink buffers and uses its history to derive the optimal TDD configuration. For instance, the default one is 6 downlink slots and 3 uplink slots. Let's try to send the maximum in this configuration, which is more or less 30 megabits per second. Then the XUp will allocate more uplink slots than downlink slots. As you see, it selects the 7 uplink slots and 2 downlink slots to allow high uplink throughput. Now, on the second UE, let's try to send downlink traffic. It's 44. Let's try to send 40 megabits per second. Here, the GNodeB or the XUp will select 7 downlink slots and 2 uplink slots in order to satisfy this throughput. On the third case, let's try to send both uplink traffic on the first UE and downlink traffic on the second UE. we'll try to balance the traffic. We'll send 15 megabit per second, and here 15 megabit per second as well. Here we see that the X app will try to balance between uplink and downlink to accommodate the two traffic patterns. Sometimes it will select the full uplink configuration, sometimes the full downlink configuration, and sometimes the equilibrate configuration, which means 5 downlink slots and 4 uplink slots. Thank you for your attention.